today I'm going to talk about seismic monitoring. Thank you, Leslie. And I know many of you probably know a lot about monitoring, so hopefully there'll be something in this for everybody, including the experts. And in particular, what I'm going to talk about is how we can use seismic monitoring to improve not only our energy situation, but our environmental situation. So I'm going to start off with this map, which is, of course, a beautiful map of the world at night. And but what's very interesting about this map is the light distribution, which is a pretty good approximation for global energy use. And if you think about where the energy comes from to power all those societies, it's pretty interesting. As I'll show in a minute, most of the energy, global energy use, the mix, 80% of it is from carbon-based sources. So that's oil, gas, and coal, 80% of the world's energy use. And if you start thinking about where the energy is distributed, well, you have the U.S. here, which is obviously using a ton of energy, and most of that historically has been fueled by coal through the Appalachians and oil and gas in the Gulf Coast region. And of course, we also have Alberta with the oil and gas also supplying that region. You move over to Europe, and you've got coal through Europe and the UK and North Sea oil and gas that's powering that whole region. And when you move out into China and the Soviet Union, things are quite different. The distribution is not so, the distribution network is not so good, and we have quite a varied mix of energy source out here. And in particular, Australia is sitting down here, and as I'm going to show you later, is about to be the next major supplier of energy in the form of LNG to Asia. So we've got this global energy use, and then if we think about global economic growth, which of course requires energy, this is from the report, the EIA report, which is equivalent to the IPCC report for climate change. This is the equivalent for energy fast over the next 25, 30 years by about 300 scientists, government people, and industry people. And what you see is that over the next 20, 30 years, the energy consumption, the global economic growth is expected to almost double in North America and other parts of the world. And in Asia in particular, you have China and India here, that growth is expected to almost quadruple. So where's the energy going to come from to fuel that growth? Well, if you take a look at what the global energy mix looks like, particular concentrate on the center one, which is close to now, and then out about 25 years, what you notice is the whole size of the pie is approximately needs to double, so the amount of energy that we require has to double over the next 20 or so years. And what you also notice is that the red part of the pie is all carbon-based. And you can see it's about 80%, and that doesn't change. The best minds are predicting in the next 20, 30 years that is not going to change. In fact, it might even grow a little bit. And you can see that 80% of that energy supply is going to have to come from oil, natural gas, and coal. You also see that the alternative energy sources, wind, solar, geothermal, hydroelectric, nuclear, etc., they are growing, but unfortunately they're not keeping pace with world demand. So we're going to have to rely on carbon-based energy sources for at least several decades, and perhaps buying us time until we get these alternate energy sources really up to capacity. The other thing that's interesting, if you look at this pie chart, the portion related to oil is shrinking a little bit, and that's because whether we're at the oil peak or just crossing over, the oil component of that is predicted to shrink over time, which is going to put more pressure on developing natural gas, and we'll be using coal more. And of course, this has implications for environmental concerns. So two of the major geoscience challenges I see going forward are, number one, how do we maximize efficient recovery of hydrocarbons? Because it is a finite resource. We're going to need it over the next several decades while we develop alternative energy sources. So we better be efficient about that. And we all know numbers of how efficient we are at recovering, how much recoverable we do recover. That's a bad sentence. You know, we're somewhere maybe around 50% or even less global average. If we could get that efficiency way up, that would be a huge deal to supplying future energy sources. The other side of the equation is, while we're maximizing recovery, we want to minimize environmental impact, particularly greenhouse gas impact, and I know that's a big topic up here as well, in terms of CO2 and environmental impact related to oil, gas, LNG, and coal-fired power plants. So, those are two major challenges. What's the problem? Why are those not easy challenges to solve? And the reason is, as geophysicists, we know we don't really have a good handle on what's happening in the reservoir, typically. So here's a map view from a project, which I'll show you a little bit more data in a minute. And of course, as usual, we might have a couple of wells there, and we might know a lot about what's happening at those wells. We've got logs, we can measure pressure, temperature, fluids in the well. We've got a lot of information at the wells. But of course, we're always interested to know what's happening between the wells, and that's where the complications start. And by the way, this is a pretty canonical problem. This could be a water injector in an oil producer. It could be a CO2 injector that's injecting CO2 for CO2 sequestration, and the producer might be a water maintenance well, pressure maintenance well. It could be a steam injection. It could be a near-surface environmental remediation program where you're injecting water or steam or something to drive out contaminants in groundwater. So this monitoring stuff we're going to look at has a wide range of applications. So what's happening in the reservoir? So the era of 3D seismic has been great, and we've been in a kind of a paradigm the last 10, 20 years since the adoption of 3D seismic. And the paradigm is that we do the best job we can to build and characterize a 3D model of the Earth, and then we predict where the fluids are going to flow. And here's an example. So now, of course, we've got the two wells. Well, we filled in a lot of extra information. We've got faults. We've got structure. We see there's oil up here. There's oil-water contact. And here's a gas injector. And in this project, gas is injecting from this well, and from the best model we could build from the available data, that gas was predicted to flow more or less up along this path to the well. Of course, it didn't arrive when it was supposed to, so everybody was wondering what's going on. And so we took another snapshot on the project, and lo and behold, there's the gas. It did start heading northwards, but found a high permeable channel that nobody knew about, because you can't really tell anything in the first 3D image about that. Turned the corner, crossed a fault that was supposed to be sealing. The pressures on either side of that, original pressures on either side of that fault were different. So it crossed a fault that was supposed to be sealing, and in fact it crossed at a spill point which we didn't know existed because we didn't have the depth structure exactly right either. So changed the fault properties, the structure, spill point, pooled into a secondary little gas cap, and flowed along this fault block finally to the producer. That's a kind of surprise that we're seeing all the time when we directly try to monitor fluids. So we do our best job we can building and characterizing models and predicting flow, but we shouldn't fool ourselves that we have the thing always well enough understood that our predictions will be accurate. So that's the power of monitoring. So let's step back a little bit and talk about how it works and when it won't work. We always, as geophysicists, talk about impedance, seismic measuring impedance, but I like to think about compressibility. Really, seismic waves are measuring a lot of things about rocks, but the number one thing they measure is the compressibility of rocks. And that compressibility is sensitive first to the rock properties themselves, and I use this diagram for myself, really, to remind myself that a rock is like a porous rock is like a sponge, and when you talk about the compressibility being sensitive to rock properties, that's like, you can buy a soft sponge that's very easy to squish, or you can buy some of those sponges that are rock hard you can whack on the table, right? The same thing with rocks. You can have very soft rocks that you can compress in your hand right up to very stiff rocks. So the compressibility that seismic waves measure is sensitive to rock properties. It's also sensitive to pore fluids. The compressibility of pore fluids varies quite a bit, particularly oil. So you go from water, salty water, which is pretty stiff, to heavy oil is pretty stiff, down to high GOR oil, which is pretty compressible, and gas, of course, super compressible. And CO2 is all over the map, as I'll show you in a minute. It's also sensitive to the pore pressure. So if you have low pore pressure in the rock, you've got a stiff rock. As you start to increase the pore pressure, you kind of inflate the rock and soften it until, of course, you keep increasing the pressure, and you hit a frac point, and the rock will fail. It's so weak. So that's what we're measuring. That's what waves are measuring. So to get a good 4D signal, that 4D signal is sensitive to the rock and fluid properties, and this is a handy little cartoon. So along this axis I have the rock compressibility, how stiff or soft is the rock, and along this axis I have what's the fluid compressibility contrast, because we're trying to detect one fluid from another, or more. So down here where we have 0, which means we have 0 rock compressibility, I mean that's a super stiff rock, and no fluid compressibility contrast, so we can't tell one fluid from another, we get a very weak signal. If we go to the opposite extreme, we have a very compressible rock, very soft, like a turbidite sand, and we have strong fluid compressibility contrast, let's say between gas and water, for example, then we're going to get a very strong signal. And in the middle is what I call the 4D sweet spot, where we've got sort of medium properties where we can actually see the signal above the noise level. I've drawn in the 4D noise envelope right here. So in the middle, it's above noise level. We get a good signal, but it's not so strong that it gets complicated. We can actually interpret the 4D data sets pretty reasonably well. What I'm going to talk about moving forward in 4D is that the challenges are pushing this noise envelope down so we can see these weaker signals, for example, fluids and carbonates or cemented sands. But also, maybe counterintuitively, there's some big challenges out here where we have signals so strong that we get extremely complex wave fields, and I'll show you some of that. So the first part, how do we beat down the noise so that we can see smaller and smaller signals? Well, what are these sources of noise? It's non-repeatable noise, the fact that we can't repeat the experiment exactly each time. So sources of non-repeatable noise that we can improve are things like source and receiver positioning errors. Also, effects in the water column or near surface. We can measure those, do a lot more than we currently do to measure those accurately, incorporate them in the processing model. And also variations in the source and receiver responses, which again, we could do a lot more effort to measure waveforms on a shot basis, etc., and receiver functions on a receiver basis. So we can do a lot more, and that's one of the future areas to bring down the 4D noise level to be able to see weaker signals. But let's also not forget that there are some factors that are beyond our control to non-repeatable noise, things like weather conditions, ambient noise, and even unexpected changes in the overburden that we don't know anything about. So here's an example of reducing non-repeatable noise. It's a Statoil example. I've worked quite a bit with Statoil Research Lab and assets over the years. And at first we're looking at a migrated section, and then beside it in the middle, the difference. And this is a difference image obtained by pretty conventional 4D processing flow, which is a parallel flow, which is to use the same flow with the same parameters and process the data through the same way. And what you see here is you get some differences in the image. It's not zero. It should be identically zero because there's no production here between these two surveys. What you find is if instead you correctly measure the tidal effect and the water column effects and apply them deterministically instead of statistically estimating them from the data, you can get a much cleaner difference section, and therefore you'd be able to chase smaller and smaller signals. So there's a lot more we can do in this area, as I mentioned, with regard to measuring properties in the water column, in the near surface, etc., and applying them deterministically in our processing flow. The other side of the equation is enhancing the 4D signal. So I'm just talking about decreasing the noise, but we could also develop smarter imaging algorithms to enhance the signal. And here's an example. In fact, this is one pretty close to you here. This is from Weyburn. And so these are carbonate sections, and this is the first survey, 99 survey, and then I'm showing the difference section. And again, this difference section is pretty noisy. Well, actually, the noise level is pretty small. NRMS would be down around 20%, which normally we'd say is very good. The problem is that the signal, the 4D signal, is even weaker than that, and so you don't see it very well here. That's because these two data sets were processed in parallel using the same processing flow. But let's imagine you had 10 repeat data sets. You could look at this another way and say, well, look, I have 10 data sets, and I could image process them all together, merge them all together, and solve it like a global optimization, global imaging problem, instead of each one individually. Solve them all together, and then I'll get new algorithms which are constrained by some parts of the Earth aren't changing and other parts of the Earth are changing, and you get a much stronger solution. And in fact, that's what's behind this simultaneous difference you see here. Same data, it's just that that concept that I talked about is being applied here, and now the anomalies pop out very nice and clean. And in fact, here's a little bit of a amplitude map along the surface. This was from the sort of conventional 4D processing approach. It's pretty noisy, or at least the signal is smaller than the noise. And then over here is this new type of simultaneous processing where you merge data sets together and have new algorithms. And you can see very clearly that you've enhanced the signal. So I was talking about the weak area and how do we push down the noise and how do we enhance weak signals. Now let me talk about this troublesome area, which doesn't seem like it should be troublesome, where we have very strong signals. And a classic example of this is the Sleipner project, which I've worked on for several years. Sleipner is a big CO2 sequestration project operated by Statoil Hydro in the North Sea. And so what you're looking at is a cross-section here. This is the top of the Utsira sand, the CO. There's the base, before any CO2 injection, after CO2 injection, and over time you see the big changes due to CO2. And of course, after the first one, with the sand lighting up, everybody's popping champagne bottles and so forth. But then after a while, you start looking and going, well, what the heck is actually going on there? And you can see it looks pretty complicated. There's multiple layers that come and go as you look through these images. We've got the so-called CO2 chimneys, which I don't believe are chimneys at all. I recognize these from the old steam projects. We used to see the same thing. They're imaging artifacts. So this is a case where you take a sand, which starts off, it's a saline sand, it has a velocity about 2 kilometers per second. You inject CO2 at those supercritical conditions, and it drops down to about 1 kilometer a second. That is a huge change in velocity, and you know you're going to get all kinds of crazy wave fields rattling around inside there. And here's a smoking gun. It's not easy to find this, but I found this particular one. Here's the top CO2 layer, and lo and behold, when we've got an overhang, we can actually start to see some of this stuff that, when you're looking in the center part, you can't tell whether you got a problem or not. But over here, there's problem. There's complexity going on. And so, in fact, to test this theory, my group and I built a 3D model based on the Sleipner Seismic, and we injected CO2 into this model, first one layer at the top and then a second layer just below, just to see what the effects would be. And here's an example of finite difference elastic shot gather. So we shot a survey over this model. Here's a elastic shot gather before CO2 injection. In the middle is the difference of the shot gathers, okay, T1 minus T0. So this difference, if it is all due to one layer of CO2, well, wait a minute. If you were thinking about convolutional modeling, if you had one layer of CO2, you'd expect to see one hyperbola there, right? No, it's super complicated because you get all the interbed multiples and conversions rattling around in there. So if this is all of this is caused, this difference is caused by one layer of CO2, that means you've got to have an imaging algorithm that knows how to take all of this and image it into one CO2 layer. You can see that's not going to be easy. And here we go, there's two layers of CO2, and you can see it just gets richer and richer. So in fact, we took this, to make a long story short, we took this and ran it through a state-of-the-art pre-stack depth migration, velocity analysis, and so forth, hit it with the top of everything, and got to this. And here's the synthetic data, the fine image. There's the one layer of CO2 at the top, plus we've got some artifacts in there because our imaging algorithms can't perfectly reconstruct that wave field. And lo and behold, this is the real difference data from the first survey, and when you look at it, it's not that different. Now, the thing is that people are taking this side, the real interpreting as that many multiples layers of CO2. But it may not be, because this one only has one layer of CO2 in it. So this is a case where we have very strong signals, we get very complex wave fields, and we need more research on how to optimize our images in those cases. So now we jump to using 4D seismic to optimize hydrocarbon recovery, now that we have all the basics in hand. And I got into this business in the early 90s monitoring steam. And in fact, the first project I was involved in, we had one small pilot area in Indonesia at the Duri field. And we didn't know if we'd see steam or not. This is with Chevron. And lo and behold, we saw the effects of steam, and that has now grown into a major operation where they routinely, every 12 or 18 months, conduct huge 4D surveys to monitor steam. And you can see very nicely here in all these patterns, you can see steam, where it's going, a lot of information in here. You can see the flanks are not taking steam so well. You can see nice patterns where steam is spreading out circularly. You're going to get a high recovery factor for that pattern. You can see other ones like these two, which are breaking through north-south, and as soon as they break through to the producer, you've essentially got a short circuit there, and you're going to leave behind 80% of the oil, etc. And this all came about because after years and years of trying to build a model and do thermal simulations to try to predict where steam would go, it just never worked. And so now we're in a mode where we're monitoring it directly. By the way, at that time, which is some time ago, 10 plus years ago, at Duri they were spending over $1 million per day to generate steam. So you can see that's very expensive stuff, and you want to make sure it's going the right place. Today that number is probably up $4 or $5 million per day. Here's the Gulfax field. Again, done a lot of work on this with Statoil. And here's a map from time one. So we're looking at, and all the hot stuff is hydrocarbons. And then, of course, if you watch in the circles, when we repeat the survey, you can see regions turning bluer. So we're watching the oil-water contact move and watching injected water where it's flowing. Each of these wells out here, you can see the platform in the wells, cost on the order of $50 million or more per well. So you can see that, and one of these 3D surveys costs about $10 million, so you can see that the leverage is pretty high. And, of course, we can make a difference. If we've got images, we can make differences. And in this case, this, although it's noisy, and we get back to signal and noise again, although it's noisy, we do see where the injected water and where the aquifer has moved, which is very important information. And Statoil states publicly that 4D has added $1 billion worth of value at Gulfax alone, and on the order of $4 to $5 billion on all the North Sea fields that they're monitoring. So the potential is huge. This is a nice example. I teach various 4D courses. In fact, I'm giving a 2-day course starting tomorrow, but the long version I actually teach for 2 weeks. And I lecture in the mornings, and the asset teams bring their data, and they work on them in the afternoons. And by the time we're at the end of the 2 week, they have a full presentation of what to do with their 4D data and where to drill and stuff. And this is a very nice example for me, because I was teaching this course in Brazil, in Petrobras, and this asset team, which happened to be the Marlin asset team, we got this map, and all of a sudden there was a bunch of excited talk in Portuguese, which I didn't know what the heck was going on. But it turns out in a matter of a few weeks they're about to drill a well up here, and this map is showing that it's flooded or quite water swept. So they were very excited and managed to move the location down to here, and this came in as a very good producer. I don't know if they drilled the one up there, if it would have been good or hit water, but it's a lot lower risk well to drill the other one. So that was kind of a nice real-time example in the course. Here's an example. I had nothing to do with this particular example, all the other ones I've worked on. But I like this one. This is in the Dan field, a chalk reservoir in the North Sea in Denmark. And what you're seeing here is long horizontal water injectors and alternating horizontal producers. And this is a chalk reservoir which has low permeability, but the model was that it's all connected up with fractures, so you drill all the horizontal wells, perpendicular fractures, connect it all up, you're going to get good flow. But you can see the 4D is showing that's not happening. The water is staying very close to the injectors, and in fact on the periphery we're getting red popping out because the producers are depleting the pressure, they're not getting water support, and gas is popping out of solution. This image shows very nicely how well or not how well your reservoir model and assumptions are working there, in terms of the water staying pretty close to the injectors and not doing a great job supporting the producers. And then, of course, as 4D is getting more and more precision, we're moving to permanent arrays. This is an example from the Valhall field, permanent array at Valhall. These repeat images. And we have 2 horizontal wells here. The top one is a producing well, and the bottom one is an injection well, which hasn't started injecting in this picture yet. And then you can see over time as the injector kicks in, you see a lot of detail both from the production well and the injection well. In fact, you notice that the injection well doesn't seem to be injecting uniform quality along the whole length of the well here. And that's actually can be used to high grade and design your workover plan for your well. So that's pretty high resolution stuff. Now, one thing I want to know, does that time count against me, or? Okay, good. And kind of the challenges going forward are, how do we take this data and use it to upgrade our reservoir model? Because, of course, we're talking about this paradigm of building a 3D model and making predictions of fluid flow. Well, just because we go to direct monitoring of fluid flow doesn't mean we should throw the model away. No way. What we should do is combine the monitoring data with the 3D model so that we get a much better reservoir model, and therefore our predictions going forward should be a lot better. And here's an example that we did with the group in Petrobras. And on the leftmost side here, or my left, what you're looking at is a map of water injection, injected water from 4D seismic. And you can see lots and lots of wells there. And so don't let anybody ever tell you, oh, we've got so many wells that there's, nothing else could possibly be happening. No, that's not true. There's always something happening between the wells. And what you notice is this water is not spreading out circular from the injectors. In fact, it has a very long direction in this way. And the geologists on this program, on this project said, well, we could have told you that. This is turbidite flow, and that's the direction of turbidite deposition. But of course, that information got lost in the history, and the engineers, when they built the reservoir model and history match it, promptly threw that out, because it didn't fit their view of the world. But we see it here. The water is flowing in an anisotropic direction. So all we did is something pretty simple. We put red arrows on there, and those red arrows, the direction shows the direction of water flow, and the length of the arrow is proportional to the permeability. So in other words, if it flowed farther, then it must be more permeable in that direction. So that gives us sort of a permeability magnitude and direction. If we use those arrows as a soft constraint on the original permeability model, which is in the middle, those original perms are kriged from all those wells where there's DST data. So they're kriged, they all fit the wells. We then add the constraint that it must fit these arrows from the 4D, and you get this new permeability model over here. And this new permeability model also honors all the DST data, but it additionally honors the 4D where the water's flowing. And you can see it has that fabric in it. And when you use this model, suddenly, after years of not being able to history match production in there on both an individual well basis and a field-wide basis, the history match improved dramatically. So what are we looking at here? This is water cut on the vertical axis over time, over years. And the blue dots are the actual measured water cut in this single well, this particular well. And you can see that the blue curve was the original reservoir model, not the original one, but the one just before we conducted this 4D experiment. And we could never get the water to arrive fast enough at that particular well. But by changing that permeability model, this happened all over a period of about 3-4 weeks after years of trying to match this reservoir. 3 or 4 weeks working with those data, we were able to get that history match very well. And on a field-wide basis, it's the same story. You can see at the early time, both the original model and the new one matched the water cut very well. And that's because when you're in the early days of production, you haven't really probed out and sort of felt much of the reservoir yet. You haven't ran into much complexity. But over time, what often happens is as you, say, inject more than a pore volume or something like around that, you get into the complicated stuff, and your reservoir model turns into kind of a Frankenstein. It's got permeability multipliers out the kazoo and very unrealistic geological things, and you get to a state pretty quickly where you cannot update that model anymore. And that's what happened here. And you could see they lost it completely, could not match for many years. And then we came along with the 4D stuff, updated that permeability field, and got a good match pretty well. Pretty easily. Now I'm going to switch gears from, the first part of the challenge was efficient recovery. So you can see how this stuff can increase our efficiency tremendously in hydrocarbon recovery. Let's switch over to CO2 sequestration, and in particular I'm going to tell you a little bit about what's going on in Australia. So as many of you may know, CO2 sequestration, or at least geosequestration, is the idea to capture CO2 from some source. Now that source might be an LNG plant, because when you liquefy natural gas, you have to remove all of the CO2. It has to be pretty pure before you can cool it and liquefy it. So it could be an LNG plant, it could be a coal-fired power station, it could be an agricultural industrial facility. There's a project going on in Illinois where AMD has got a corn processing plant, and until I learned about this project, I had no idea what you could make out of corn. I mean, they're putting corn in, and cars are coming out the other end practically. It's amazing, but it generates a ton of CO2. Some of it's food quality grade, but a lot of it's not. Other place, tar sands. I know you generate a lot of CO2 regard to this tar sands. So the idea is capture it at the source, separate CO2 from whatever the other products are in the stream, compress that CO2, pipe it somewhere, and inject it back into the earth where it came from. And of course, the idea is to inject it usually at least 1 kilometer or more depth, where it's supercritical, and you inject it into a porous permeable formation. It might be have traps and so forth. It might be a depleted oil field, but actually there's about 1,000 times more storage opportunity in saline aquifers. So this whole concept is gaining a lot of energy And countries around the world are scrambling to map out where are potential places to inject and store CO2. And Australia is no different. This is a map that's come out recently from Australia. This is a map of all the basins around Australia. The green ones have very good storage potential for CO2, and down to the red ones, which are bad for storing CO2. And recently, about 2 months ago, Australia became the first country in the world to actually lease offshore blocks, like you would lease them for exploring for oil or minerals, to lease offshore blocks to explore for CO2 storage sites. So they're anticipating there's going to be a big business in this. And if I zoom out on Western Australia, where I am presently, Perth is right here, there's some pretty exciting things going on. So first of all, off the Northwest Shelf, there are major gas fields which are just about to come into production. And the first one is Gorgon Field. You may have read about it. Gorgon is a giant gas field. There's about 50 years of production there. Just received FID a couple of weeks ago. Chevron's the operator, and Shell and ExxonMobil are partners. $50 billion project. And I'll talk a little bit more about it. They're going to build an LNG facility on Barrow Island, which is a Class A nature reserve, and inject the CO2. There's about 14% CO2 in the gas there. Inject it beneath Barrow Island. But there's a whole bunch of other projects. Wheatstone, Pluto is a large Woodside project. A bunch Shell and Woodside in the Browse. There's at least about, of the ones that the companies are comfortable enough to give numbers on and so forth, say they're going to develop. There's $200 to $250 billion worth of investment that's about to kick off in these giant gas fields. And all of them have CO2 issues, whether they contain a lot of CO2 naturally or even if they're only 1 or 2%, because they're all going to be LNG, that's got to be removed to cool and compress the gas to LNG, and something has to be done with it. The other thing that's going on is Australia, like most countries in the world, Canada's a little bit different, but most countries in the world generate their power by burning coal. And Australia has a lot of coal, and that's how most of the power is generated. So we've got a project, it's in the proposal stage right now, at Koolimba, just a couple hours north of Perth. It's a $1 billion project to build a zero-emission, clean, coal-fired power plant. So the CO2 is going to be captured, on site and injected somewhere. And of course you can see you want to put that plant somewhere near where the green basins are, where you have somewhere to store it potentially. The other thing that's another thing that's close to home and is the Collie region. Down in Collie, there's a bunch of major power plants, all coal burning, and they supply most of the power to Western Australia. And so these red little boxes are all existing coal-fired power plants. And together, they generate 15 megatons of CO2 per year, which is a significant percentage of all of Western Australia's CO2 emissions. And so there's an idea kicking around that we're trying to get funding for. You could build a pipeline to connect them all together, capture the CO2, and inject it somewhere nearby in a deep formation. So there's a lot of interest around this, and as I've given talks at various societies, for the first time in my life, the guys from the coal companies are coming up and asking questions because they're very worried about their industry. If they're going to run into carbon tax or cap and trade, whatever it is, they're worried they're not going to be able to sell their coal in the future. And so the coal companies have come together, pulled together, and made a research fund of $300 million, which for me is huge, considering Australia is about half the population of Canada. $300 million to go into CO2 CCS research because they see what's coming down the pipe, so to speak. Okay, now a little bit about this Gorgon CO2 sequestration project. So it's offshore, northwest shelf of Australia. It's actually a collection of several large gas fields. Mainly Gorgon and Jansz. And the gas production is going to be, they're building a pipeline along the seafloor that comes up to this Barrow Island. Barrow Island is a Class A nature reserve. And there'll be, so it's very important to protect the integrity of the nature reserve there. and then the CO2 will be injected below the island. Here's a picture of this island. It's a pretty small island, and it has a lot of species which are native only to that island. There are turtle breeding grounds around the edge and so forth. It's a terrific place. So the concept is to build a very low impact, light footprint LNG facility there, and the ships will, I know it sounds counterintuitive, but in fact, let me say that in the southern part of the island, there's actually a producing oil field there, and it's been there since the 60s, and it meets all the top standards. The government environmentalists are all very happy with it. Before any equipment goes out there, I should have brought some pictures. For example, if you got to move a truck out there, that truck has to be sterilized at the factory it comes from, has to be essentially saran wrapped, and then shipped out there, where they do a test again when it arrives, and if its integrity has been broken, they send it back to do it again. So the standards are super, super high, and they've been doing that for a couple of decades. So this LNG plant's going to be out there. Again, 14% CO2 in the gas stream, produced gas stream. So what they're going to do is inject, separate it on Barrow Island, inject it beneath. And here we are. It's going to be injected down in the Dupuy Formation down here. And you can see that there's several sands and thick shale sections, so there are multiple seals before you get to the surface, so that if for some reason it ever did migrate out of its original location, the injected CO2, it's got lots and lots of barriers to pass through. And here's a blow up down here. In fact, the sand itself is not one large clean sand. It has many shale lenses in it, which actually helps store CO2, because CO2 is very buoyant. If you have a clean sand, the CO2 wants to rise up to the top very quickly and only fills up the top part of the sand. If you have a lot of shales interspersed in there, it sort of causes a dispersive baffling effect, and you can fill up more of the volume to store the CO2. And they're right now in the middle of acquiring a baseline survey. And of course, again, this is a Class A nature reserve, and so it's very tight specs on what you can do out there. So Chevron has done a bunch of excellent field testing on different source types and geophone types. Here's a little bit of lay of the land. So you can't really drive many vehicles around there, so most of the stuff is going to be brought in on foot. And in fact, about 50% of the positions will be helicoptered in, lowering the source or receiver, picking it up and moving off again. So it's a pretty amazing operation. Now CO2, as we know, it's stored in rock. I still have to try to convince some members of my family that oil and gas and CO2 are not just found in a huge cavern underground. It goes into rock like this core sample. And just to remind us, so the CO2 is going to get into the pore space, and it's trapped by a variety of mechanisms. Of course, you inject the CO2 in there, you have residual trapping due to capillary pressure, then the CO2 dissolves into the water, and finally, that's over tens of years, and then over hundreds of years it precipitates as a mineral. So the properties of CO2 vary strongly with pressure and temperature, and here's a map. This is the phase space, pressure, and temperature of CO2, but I'm plotting the bulk modulus, or the stiffness of pure CO2, and you can see that it varies by an order of magnitude across this potential range. So the properties of CO2, the compressor, really vary a lot depending on exactly the pressure and temperature you're at. Also the density, here's a plot of the density of CO2 as a function of pressure and temperature, and also the density varies about an order of magnitude, from something very much like gas, free gas, to something right up close to oil. And as we inject CO2 into the rocks, well, we want to predict what happens to the saturated rock properties. So here's velocity and density, etc., changing as we inject CO2. And you get the we think we get the classic Domenico or Gassman effect, whereas you start to inject something compressible like gas or CO2, then quickly the compressibility of the rock increases, or the stiffness drops off. and then levels off. And there's two interesting things about this. One is, what's the minimum amount of CO2 before you could detect it? And sort of the most optimistic numbers might be around 1% CO2 if you follow this curve, or a few percent CO2. Well, that's a big issue, because if you had CO2 leaking out of a storage reservoir, and it was leaking out in small amounts, 1 or 2%, we wouldn't be able to detect that seismically unless it pooled up somewhere. The other thing that's interesting about this curve is, as it levels off, you can't tell 30% CO2 from 80% CO2. Well, what's the problem with that? This is a little bit like your bank account. You know you put money in there, $1,000 in there, you know it, the bank knows it, but you want to go in and actually check it's there, right? That's what regulators are going to want us to do. They'll say, fine, you measured at the surface, you put so much CO2 in, but show me it's actually down there and calculate the mass from geophysical images or other techniques. That's going to be really tough to do if you're facing this curve. But is that the right curve? And we're not sure. And here's some data from the CO2 pilot test in Japan, Nagaoka. And what these blue dots are repeated logging. So it's not at surface seismic frequencies, but it's at kilohertz or tens of kilohertz. And you see that these dots are not following that Domenico curve. So there's a lot of interest in patchy saturation and how the fluids are distributed. And of course, it's a frequency-dependent effect. So we see this effect in core data at sort of megahertz. Now we're seeing it with CO2 in log data. So we really need a little bit more work to convince ourselves that we're surface seismic 10 to 100 hertz. We're following this curve. Of course, it makes a big difference if it does or doesn't. The other thing so CO2 is very complicated, and it's chemically reactive, and we really haven't looked into that too much at all. And here are some very recent measurements from Stanford Rock Physics Group. And what you're seeing here are measurements of velocity with repeated injections of CO2. The solid dots are saturated, when they're saturated with CO2. The open dots are when they dry the core out again after CO2 and make another measurement. And what's clear, that the dry samples are changing as a function of CO2. In other words, the CO2 has got in there, is chemically reacting with the rock and weakening it. And that's a huge amount. If you do some quick computations there, that's 15-20% over just a few weeks of CO2 injection. So does this actually happen in the field? I've been seeing this for years by monitoring CO2 EOR projects. We've been seeing it in the 4D seismic data, and the geochem guys said, no, that's not going to happen for tens or hundreds of years. But now, in some of these CO2 test projects, they're actually in many boreholes measuring fluid samples. And here's an example. This is from Weyburn, showing carbon isotope at the top, calcium in the fluid, and alkalinity, or related to pH. And this is early during injection of CO2 at Weyburn. And then the ones on the right are after quite some time of injection, and you see huge responses in the chemistry. So in other words, the CO2 is reacting. In this case, it's with carbonates. You get CO2, gets into water, carbonic acid, starts reacting with the minerals. This is not just for carbonates. We've seen this in sands too, when it's dissolving the cement, calcite cement around grains, and even when it's not cemented, when you just have carbonate grains in the matrix, it's causing effect. And we really have no idea how to deal with this or predict it right now. So when you get to Weyburn CO2 images, such as these ones, and you see yellow is injected CO2, or we think it's CO2, but actually trying to quantify that, if you think about the Domenico curve, how much CO2 is there, what's the effect of pressure in these images, and what about the geochemical effect, you can see it's very tricky to try to quantify from these images how much CO2 is there. So that gets us, how can we beat Gassman, if we ever can, or Domenico? Well, we should think about other geophysical techniques as well. And gravity is one to think about. Notice this is P-wave velocity, but the blue curve is density. And the density of the CO2 saturated rock varies pretty linearly with CO2. And in fact, in this particular rock, it's up to 10% change in density. Well, we might be able to measure that with gravity instruments if the reservoir is pretty close to the surface or if we get borehole gravity sensors. And here's a synthetic example showing a CO2 injection simulation on this side and the gravitational response here. And gravity data is getting pretty good. We're down about 3 microgal noise threshold, and some of these CO2 projects are expected to give maybe 10 microgals or so response. So that's a very interesting thing to look at. Now gravity, and I'll show you EM in a second, they're very low resolution techniques. But if we use the seismic for the high resolution to show where the stuff is changing, and then did a gravity inversion and constrained it to where the seismic said things were changing, you might have a very nice quantitative result. And that's research I'm actively involved in. The other thing is CO2 is resistive. And so here's Archie's law showing resistivity versus a function of gas saturation. There are, logarithmic changes in resistivity as a function of CO2 saturation. And of course, controlled source EM or any other type of EM technique has the ability, as we know, to detect, it could detect changes in resistivity in the reservoir. And so there's some things going on right now. In fact, the Scripps research vessel from Scripps in Southern California was just out in Australia in May, June, shooting a bunch of offshore time-lapse CSEM tests to measure repeatability and so forth. So that's a pretty exciting area to take a look at, too. Last couple of things as I wrap up here is passive microseismic, and I know there's a lot of interesting work going on up here, but so here we are, either passively recording, listening to microearthquakes, which do occur during CO2 injection in some reservoirs. Here's a very interesting example conducted by Jim Rutledge at Los Alamos National Lab. The blue dots are microearthquakes located from a well during CO2 injection in an EOR project. These blue dots are seem to be correlating with the front of CO2. So 4D seismic, we use it to see kind of where the main saturation change has been. Microseismic tends to respond to the pressure gradient at the front of the front, so to speak. But also, there's some other microseismic events over here, and these are thought to be some slight reactivation of a fault due to pressure changes in here. And in fact, there was a sizable earthquake that occurred during the CO2 injection. And here what you're looking at is production in this oil field, which jumped right after the earthquake, so it changed the flow characteristics of the reservoir. And the amount of microseismicity jumped considerably after this earthquake too. The interesting thing is this array was used to prove, this microseismic array, passive array, was used to prove that the earthquake was outside of the reservoir and not related to what was going on in the reservoir. It somehow affected the permeability structure, but it was not related. And I think this is going to be huge. If I was operating a CO2 injection project, I would put out passive arrays just as an insurance policy, because you know it's going to happen, right? You're injecting CO2. If an earthquake does happen, who are they going to blame? So just as insurance policy, I think we're going to see a lot more passive arrays out there, to forewarn of any fault reactivation and so forth that might be going on in the reservoir, and B, to prove if indeed the earthquake is not related to injection. And last slide is radar data. Some of you may have seen this from INSAR in Algeria, CO2 project. The great thing about radar data, it costs about $5,000 an image. So you can see some things on a 30-day basis, 30-day turnover, very cheaply, might give you an early warning system of some things happening down in the reservoir. At Installer, the CO2 is injected at about 2 kilometers depth, but in fact, you see the surface of the Earth moving, deformation on the surface, up to about 5 millimeters a year, which is picked up by the satellite data. And here we are, these are CO2 injectors, and you see these changes in the ground surface, and what you notice about them, so they're going to be related to pressure change in the reservoir, not CO2 directly, but pressure. And you see they're not asymmetric, right? They're not spreading out spherically or circularly around the wells, telling you something. In fact, your eye can almost draw a line through here. There's probably a fault here, and they probably know that, but this says that fault is probably sealing over here. Down here, life is getting a little more complicated. And again, if you look at this satellite data over time, you see it building up, and you can see these anomalies are quite asymmetric. That's probably the sealing part of the fault running through here. It switches to baffling, which means it's partially permeable, and there seems to be an antithetic fault that runs this way. You've got two little anomalies either side of it. So even though this data is not exactly 100% showing you CO2 or pressure, it only cost about $5,000 a pop, and you can have it every month. So we're looking for ways like passive seismic and like radar to get some surveys in between our big $10 million surveys, which might happen every year or two, to link things up in early warning systems and so forth. So my last slide is I'm setting up a new research center at the university. In fact, we're having our kickoff meeting the end of November here. Anybody interested in participating in this research or collaborating with us, be happy to chat with you about it. And I'll leave it at that. Thanks.